So Isaac Newton throws an apple into the air at the top of its projectile. The apple stops momentarily, returning to the ground. Draw a labeled free body diagram to represent all the forces on the apple at the point at the top of its projectile. Well, firstly I need a circle. Then I need a downward arrow, and that's your gravitational force. And then many of you put in air friction. This apple isn't moving. If it isn't moving, it's got no air friction at that particular point. So you lose marks for any extra forces you put in. We've got a skydiver. He has a weight of 700 newtons, so you can either write weight or gravitational force downwards. He is going at a constant terminal velocity. That means that the forces on him must be balanced. So those two lines must be exactly equal, and that is air friction or air resistance. And finally, draw a labeled free body diagram of a bullet that has just left the barrel of a gun. It has left the barrel. It has no forces acting on it forwards or backwards. There is a downward force, gravitational acceleration. And then acting against it falling and going forwards is a smaller arrow, so that one should be bigger, smaller, and that is your air friction. I didn't make a big deal about the fact that air friction should have a bit of an angle to it. If you just did it backwards, that was absolutely fine. A 1,500 kilogram block is at rest on a rough horizontal surface. The coefficient of static friction is 0.26. What's the maximum static friction on the block? Now, you'll remember that frictional force is equal to mu F normal. Since this is a perfectly horizontal block, the downward force of weight is exactly equal to the normal force. So therefore, you can work out that force of weight. It's 1,5 multiplied by 9,8. Don't forget, this 1,500 grams is 1,5 kilograms, and so it is 0,26 times by 1,5 times by 9,8, which is equal to 3,82 newtons. A 65 kilogram crate remains at rest on an inclined plane. Its angle of inclination is 23 degrees. Determine the coefficient of static friction. So the first thing that I need to do is I need to resolve this block into its components. So this is a 65 kilogram block, which means that its weight going downwards is 637. We've then got a component acting over here, and we have a component acting down the slope, which would be equal to, on a triangle, something over there. So I'm going to just redraw this a little bit better. So I've got 637. I've got a force over here. The angle over there is 23 degrees. And I have a force down over here, and there's 90 degrees in there. This is the one that is parallel to the plane. This is the force that is perpendicular to the plane. So the force that is perpendicular to the plane is equal to the force normal, and the force that is parallel to the plane is equal to the force frictional, because this is standing still. So we can work out both those components by using trig, and we can sit here and we can say, here's my hypotenuse. If we maybe just grab another color over there, that's the hypotenuse, that's my opposite side, and that's my adjacent side. So if I'm going to start off working out the force normal, I'm going to say force normal is equal to 637 cos 23, because that is my adjacent side, and that turns out to be 586,36 newtons. Simultaneously, my frictional force is equal to 637 sine 23 degrees, and that turns out to be 248,89 newtons. Now we need to use this equation over there in order to say that mu is equal to the frictional force over the normal force, which is going to be equal to 248,89 divided by 586,36, and I land up with 0,42. State Newton's first law, State Newton's second law, and State Newton's third law are pure bookwork. So I'm simply going to Newton's first law: an object will remain at rest or at a constant velocity unless an unbalanced force acts on it. Newton's second law: if a net force acts on an object, it will accelerate, a lot of you left out this bit, in the direction of the net force. The acceleration will be directly proportional to the net force and inversely proportional to the mass of the object. And then for every action force, there's an equal but opposite reaction force. Some of you left out the words force here. That's also not acceptable. It's important to wear a safety belt in a moving vehicle. Explain how a seat belt prevents injury in terms of Newton's laws. You need to say that inertia, or Newton's first law, would carry the person forward if there was a sudden brake. Then you can go on to say that the seat belt, and this is very, very important, exerts an unbalanced force in the opposite direction to stop the person going through the windscreen. An 8-kilogram block is being pulled along a rough horizontal surface with a force of 120 newtons, which is at an angle of 25 degrees to the horizontal. This isn't an inclined plane, but you're going to use your sine and cos again, because this is 120 in that direction, so you're going to land up with a horizontal component, and you're going to land up with a vertical component, and that vertical component is equal to the opposite side over there. So if I'm labeling this triangle, there's my hypotenuse, there's my opposite, and there's my adjacent. So it first says calculate the components. So the vertical component is going to be equal to 120 sine of 25 degrees. Why? Because it's the opposite side, and that's 50,71 newtons. And then my horizontal component is equal to 120 cos of 25 degrees, and that turns out to be 108,76 newtons. Then it says determine the normal force acting on the 4-kilogram block. Well, I know that there's a downward force of 78,4 newtons. That's 8 times 9,8. And there is an upward force of 50,71. So the resultant force, the normal, this block isn't moving up or down. So therefore, we need to know that the downward force of weight is equal to the upward force of the vertical component plus the normal force. And when we substitute in 78,4 here, and we substitute in 50,71 over there, force normal is going to turn into 27,69 newtons. Now it says determine the frictional force between the block and the surface, and we know that frictional force is equal to mu force normal, so I can use my 0,28, multiply it by the normal force, and I land up with 7,75 newtons. I can now work out a resultant horizontal component. I've got 108,76 moving to the right, 7,75 moving to the left, so the resultant horizontal force is going to be 108,76 minus 7,75, and that turns out to be 101,01 newtons. Now, that is your resultant force that actually causes motion. That's the net force on this block. So we can now say that is equal to mass times acceleration. And mass times acceleration is going to be 8a is equal to 101,01, and a turns out to be equal to 12,63 meters per second squared. Last example, it said determine the tension in the string. I'm first going to work out what is happening with these two blocks. We've got two blocks, they've got masses, they're connected to a light string, smooth, no friction. What good news is that? When a force is applied to block B, the acceleration in the block is as follows. So let's go. First, only looking at block A, we can say force resultant is equal to big force. This thing's moving to the right. T minus small force, there is no friction. So we can say 4A, and we've got A. Remember, resultant force is mass times acceleration, 2,5, is equal to the tension. Oh, goody, we've got the answer. The tension is 10 newtons, so easy, without friction. And then the next one is force resultant is equal to the big force minus the little force. The force resultant is 14 times A mass times acceleration, which is 2,5, is equal to a force I do not know minus a tension I do know. And therefore, when I resolve this, the force turns out to be equal to, this turns out to be 35. So it's 35 plus 10, and that's 45 newtons.